Welcome back my dear friends. This is the TQM1 lecture series under NPTEL MOOC and I am Raghunandan Sengupta from the IME department IIT Kanpur, and we are doing the 37th lecture in this 40 lecture series for TQM1, and this is the last week for the course. If you remember in the last lecture, which is the 36th one, we were discussing about the cumulative sum of charts, and depending on the value of H and the value of C plus, which you find out whether it is greater or smaller, you find out where the trend or the change of trend has occurred, and you can comment intelligently and take corrective actions accordingly. So, considering the CUSUM charts in the final discussions. So, recommendations for CUSUM charts are: tabular CUSUM is designed by choosing the values of the reference value of K. So, K, if you remember the dispersion, positive, negative. So, values of level of confidence, so called, even though that may not be the right word. So, if it is 1, so and the standard deviation is 1, so obviously the total dispersion would be 1 divided by 2, on both sides would be half and half. If the level you want to have 2 is 2 into 1 would be 2, 2 would be divided in equal proportions onto the right and left, it would be half and half for the value of 1 and 1 the value of K. And the decision interval based on which you will take a decision whether it has crossed the limit or is below the limit is H. For the ARC example, last example we took it as 5. So, and the 29th reading, when it was 5.28, it crossed it and we gave comments accordingly. It is usually recommended that these parameters be selected to provide good average run length performance. So, generally we define H as the multiplication of small h into sigma. So, small h would basically give you the levels of confidence. So, sigma is basically the level of dispersion of 1 unit per rate consider, and what is the overall dispersion which you will have on the left hand side and right hand side would be decided. So, you will have basically defined H, capital H as small h into sigma and capital K as small k into sigma, where sigma is the standard deviation of the sample variable, and using values of H as small capital H to be calculated, we use small h as 4 or 5 and K values as 1 to 2 will generally provide a good CUSUM that would have basically a good average values properties against a shift of about 1 sigma in the total process mean. So, K is chosen to relative to the size of the shift that we want to detect. So, based on that we select the value of capital K. So, few values of K's and corresponding values of small h. So, these are small h and small k's which are chosen for a two-sided tubular CUSUM charts are as follows. For K being 0.25, small h is 8.01, for K value small k value of 0.5, capital small h is 4.77, so on and so forth. So, for K small k values of 1.5, H value would be 1.61, and all these combinations can be utilized. We will consider now the standard CUSUM charts or the cumulative sum of charts. Many users of the CUSUM prefer to standardize the variables xi before performing the calculation. So, if you standardize the variables, obviously the question will come that what are the standardization, and the best one is basically use the normal approximation. So, if you remember, and from basic probability and statistics, what we do is that we convert x, a random variable which is normally distributed with mean sigma, mean as mu and standard deviation as sigma. We use the formula as z is equal to, so let me write it. So, the z value is x minus mu suffix x by sigma suffix x. So, this x is distributed as normal mu x sigma square suffix x. Based on that, this normalization would be done. So, we are trying to use the same thing here. So, let the calculations be given in such a way that you consider y, which is the normalized new value, is equal to xi minus mu naught divided by sigma. So, mu naught is basically the target value. So, based on that, when you find it, so the standard two-sided CUSUM charts would be given accordingly. So, once you find out, if you are finding out the one-sided or two-sided depend on the x values, you basically subtracted or added the values of k, capital K, to xi's and then xi suffix I, and then did the calculation. So, in this case let me highlight it. So, these values will come accordingly. So, you can find out C plus and C minus, C suffix plus and C suffix minus, and do the calculations accordingly. So, advantages of standard CUSUM charts are, many CUSUM charts can now have the same values of K and H. So, obviously, whatever the K values are, whatever the H values are, small k and small h, you can basically standardize them and utilize them accordingly. And the choices of these parameters are not scale dependent, that is, they do not depend on the level of sigma. So, even if sigma is 1, 2, 3, 4, it will be scaled because you are dividing by sigma, and obviously finding out the difference between the actual random variable xi and its target value, which is mu naught. The second advantage is a standardized CUSUM leads naturally to a CUSUM for controlling the variability, and you can find it that is much easier to read it and understand the tables and the charts accordingly. The fast initial response or head start feature basically for this process would be, it basically aims to and improve the sensitivity of a CUSUM charts at process startup when the process starts. It basically has increased sensitivity at process startup, which would be desirable if the corrective action did not reset the mean value to its target value. And the fast initial response or head start essentially is such that it sets the starting value of C plus and C minus, suffix 0 which is the stage, the first stage, second stage, third stage, so on and so forth, which equals to some non-zero value. Typical would basically be h by 2. The reason why it is h by 2, again we are basically giving equal proportions to both positive and negative fluctuations. So, if h was 5, so C plus and C minus would be 2.5, 2.5 depending on that. So, we are considering the dispersions are same. Now, the question would come that why we are considering the dispersions are same, then again going back to the calculation of the normalization, what we did, we find out yi is equal to xi minus mu naught divided by sigma. So, obviously, this normalization being the case of trying to utilize the standard normal deviations, and obviously even though they may not basically make much sense here, we are trying to utilize the fact that the central limit theorem holds true in this case also. So, this value of finding out C plus and C minus using the value of typically h by 2, this is called 50% head start values, and we use those initial calculations. Consider an example below. So, we have the period given from 1 to 10, you have the xi values starting from 102 to 999. So, we take a value of 103 and find out the difference between xi minus and the 103 value. So, the values are given in the third column starting from -1 to -4. So, we find out the C plus values and the n plus value. N plus are the numbers of deviations which are happening. Also, we find out the differences and recalculate and the values of C minus and n minus values depending on the lower side for a value of 97. So, what you are trying to do is that you are trying to basically find out a plus and minus deviation of 3 units. So, 100 plus 3 is 103 and 100 minus 3 97. So, you are taking this value and this 97 value, trying to find out overall so called fluctuation in the average values as you take both same quantum of dispersion on, not, I will not use the word dispersion, same quantum of displacement on the positive side and the negative side. Based on that, once you have basically the fourth and the fifth column, which I am basically highlighting with yellow, and the last two columns, which is basically Ci minus Ni, C suffix minus and N suffix minus. So, they would give me the number of cumulative sums and the number on the negative side, on the lower side, and similarly the fourth and the fifth column, which is C suffix plus and N suffix plus, would give me the fluctuation on the positive sides. These data have a target value of 100. So, basically the target value was 100 and we considered k as 3. So, obviously plus minus k would give you the value of 103 and 97. H value is basically 12. So, we will use a 50% head start such that the value of C plus and C minus at 0, which is the initial values where you are starting, would be given by 12 by 2, which is 6. The first 10 would basically mean that it is basically the value we are trying to use, which means the mean equals to the target value, and the CUSUM charts are basically calculated accordingly, which is like this. Now, here I would like to again repeat, the value of 103 which you are considering is basically the positive deviation on the upper side, the value of 97 we are considering is the deviation on the lower side, and the values of C plus suffix 0 and C minus suffix 0 would be basically consider the value of 6. So, based on equal dispersion or 50% head start, we will basically take the values accordingly and recalculate and do our stepwise calculations in the similar way. The starting CUSUM values in the head start, as I just mentioned few seconds back, it is h by 2, which is 6. From period 2 onwards, C plus is unaffected by the head start, and from period 3 the onwards, C minus is unaffected by the head start. This has occurred because the process in its control and the target value is 100. So, any fluctuations which is happening does not affect the head start values for C plus and C minus values corresponding to the second and the third reading. And several consecutive observations near the target value were observed. So, obviously, they were always in process control. A CUSUM for monitoring process variability would be, let xi suffix I be the normal distribution process measurements with mean or target values given as mu naught and standard deviation given. Again, you are using the same calculation of yi is equal to xi minus mu naught divided by sigma, based on that we do the calculations. So, new standard deviations will be found out, which would basically be the y we will take mod, because mod would give me the positive and negative fluctuation in equal quantum, and these values of 0.822 and 0.3479 would basically depend on the values of n or the sample size. Here the sample size would not make much sense, but basically depending on number of such fluctuations we have on the positive side and negative side, based on that we recalculate and find out the average values and do the calculations. So, this new standard deviation, which is v suffix I, would be given by square root of mod of yi minus 0.822 divided by 0.349, which is basically the proxy with these values of the proxies for the target values and the standard deviation respectively. Since the in control distribution vi is approximately, so they are saying this is approximately a normal distributed with 0 mean and 1 standard deviation. So, this two one-sided standard scale can be established as follows as shown in the next slide. So, it will be given the scales CUSUMs would be that I am trying to utilize the standard deviation, which is vi, with plus and minus fluctuations coming from the k value. K value is basically the charts for normalizing, we have used the small h and small k. So, those k values would be utilized, and we will use this s values, which will give me the plus and minus fluctuations depending on the last reading. So, we are trying to utilize the last reading as the datum based on which we will do the calculations. The interpretation of the scale CUSUM is similar to the interpretation of the CUSUM for the mean. If the process, so scale CUSUM would basically a way of trying to basically give some information about the standard deviation. So, if the process standard deviation increases, the value of S plus will increase and eventually exceed H. H is basically the scaled value of capital H. So, capital H, if you remember in the first problem was 5, and the moment C plus value was 5.29 or 28, we say that it has increased on the positive side, and we need to basically understand where the fluctuation occurred. In the scale CUSUM values, obviously the scale values would basically compared with small h. So, small h, depending on whatever calculations you have done, we will consider that values, and moment it exceeds or it is below that value, we would be aware that at what level the changes occurred. So, continue our discussion here as it is written, the values of S plus will increase and eventually exceed H, whereas if the standard deviation decreases, the values of S minus will increase and eventually exceed H, depending on which side of the calculation which you are considering. So, rational subgroups have to be analyzed. So, although we have given the development of a tabular CUSUM for a case of individual observations, which is 1 n is equal to 1, it is easily extended to the case of averages of rational subgroups where the sample size r n is greater than 1. Simply replace xi by xi, which is the sample or the subgroup averages, in the above formula and replace sigma by square root of n. So, it is the same thing. So, you had, if I go back to the initial calculation where I will try to basically highlight. So, you had basically a population and basically you have to take a sample. So, in the population you have basically the mean and the variance which was sigma square. Now, it is best predicted which we knew, which was basically x bar. So, now what we need to do is that basically find out, this is suffix n, this is the sample size, you want to find out basically the distribution of x bar n. We know this is the distribution which is normal with mean as mu and variance as sigma square n. So, once when we are trying to basically draw the standard normal deviate for x bar n, so it will be x bar n minus mu divided by square root of sigma square by n, because this would be the corresponding standard deviation of the random variable which you are trying to analyze. So, here the random variable is x bar n. So, we will do the calculations and find out. So, that this value which I am going to now highlight with the yellow color. So, this will basically be the value of the standard deviation, which comes out to be sigma by square root of n. That is why when we are saying that we are trying to basically use sigma, replace sigma and use the value of sigma by square root of n. This is the actual concept, such that we are trying to utilize the sample characteristics, find out its distribution and use that in the normal case and find out the standard normal deviate. With Shewhart's charts, the use of averages of rational subgroups substantially improves control charts performance. However, this does not always happen with the CUSUM charts. Only if there is some significant economy of scale or some other valid reason for taking samples of size greater than unity should one consider using n is greater than 1 with CUSUM charts. One practical reason for using rational subgroups for size n greater than 1 would be that we could now set up a CUSUM on the sample variance and use it to monitor the process variability. So, what we are trying to do is that trying to basically utilize the sample variance and try to monitor the fluctuation on a scaled note, such that normalization gives us much better information and how the control charts are done. So, after the CUSUM charts, which is I do understand is a lengthy process and quite involved, we will just consider another one, which is the exponentially weighted moving average or EWMA. The control chart is also good alternative to the Shewhart's control charts, where we are interested in detecting small shifts in the overall process capability. The performance of the exponential weighted moving average charts is approximately equivalent to that of the cumulative sum control charts, and in some way it is easier to set up and operate as with the CUSUM charts. The EWMA is typically used for individual observations, and based on that we do our calculations accordingly. Now, the exponential averages would mean basically we are putting some weights on the past data. So, the level of importance you want to give the past data, as I mentioned in that example, would of the winter clothes or the fridge sale, or say for example the cooler sale, would depend on the information set, that what is the level of significance or level of importance you want to the past data. Say for example, if I am trying to utilize the information for October and November on to the prediction of, say for example January, it may be possible that I put 50% weightages on October, 50% weightages on November and do the calculations. It may also be possible that the nearer the data is, more amount of information and more amount of accuracy which we would basically gather. So, obviously, if we are able to change the overall weightages for the November data from 50% to, say for example 90%, in that case it would mean that we are putting a level of confidence of about 10% onto the October data. So, obviously, these values would fluctuate depending on what type of prediction and what type of calculation which you are trying to do. So, now another point should be remembered, that the level of importance which you are going to put on the past data need not be only the past data. That means, if you are trying to find out the actual prediction for the tth data, I may be utilizing only the t minus 1 data, but it may be possible that in many of the prediction or trying to find out the exponential moving charts, I would be able to put weightages, say for example, the first data, second data, third data, fourth data to find out what is the overall prediction overall values of, say for example, the fifth data. So, obviously, the weightages would change accordingly. So, here as it gives, I am trying to basically find out. So, this would make things much clear. So, when I am trying to utilize this equation, it means that I am trying to for the jth ith data, that means the overall fluctuation or the prediction what I am trying to do would basically give me a weightages of lambda to the random variable xi, and it will give me another weightages which is 1 minus lambda. So, say for example, lambda is 90%, 1 minus lambda would basically be 10% on the past prediction which has already occurred. So, that means we are trying to basically give less weights to the past prediction. In case, if for example, it happens that we give more weightage to the past prediction, it would mean that the data of x I suffix I minus 1, x suffix I minus 2, x suffix I minus 3 would be considered onto a much higher scale. So, here continue our topic discussion. Here the value of lambda would be between 0 and 1. The starting value required for the first sample at I is equal to 1 would be given a fixed values, and based on that fixed value the fluctuation would be considered. Now, consider that you are trying to do the studies based on, say for example, one of the iterative methods like either the Newton-Raphson method or the Runge-Kutta method. So, there you start with the seed or a initial value. So, this initial value has to be chosen for our exponential smoothing and charts or exponential weighted moving averages in such a way that they would be the best starting value based on which your exponential smoothing can be basically normalized. Normalized means that whatever weightages you are trying to find out gives you the accurate results. The target value as noted down, the z naught would basically be the mu naught value or mu suffix 0 value where you are intend to reach. Sometimes the averages of a preliminary data is used as the starting value for the exponential weighted moving average, such that z naught would basically be given an x, and we will continue calculating based on the x which is the starting value. The weightage is which is lambda 1 minus lambda to the power j decreases geometrically with the age of the sample mean. So, and it should be remembered thus weights of the sums are unity. So, since the weights decline geometrically when connected by a smooth curve, the exponential moving average is sometimes called the geometric moving average. So, what it basically means is that if I join the overall curve, it basically falls smoothly as an exponential curve. Since the exponential moving average can be viewed as a weighted average of all the past and the current observation, it is very insensitive to the normality assumption. It is therefore an ideal control charge to use with individual observations. So, obviously, normality would not be coming into the picture because you are putting weights according to the overall prediction which you want to do or overall level of importance you want to keep for different type of data. So, here we find out the weights of the past sample means, and considering the exponential moving average of lambda is 0.2, where 1 minus lambda would be obviously 0.8, the 5 period moving averages are given, and based on that we can do the calculations and do the calculation for the charts accordingly. So, in case say for example, lambda changes from 0.2 to 0.8. So, obviously, 1 minus lambda would be 0.2 and the calculations would be done accordingly. The upper control and the lower control, I am just giving the formulas for the exponential moving average charts would be given by mu naught is basically the target value. So, obviously, it would be there. The central line would be mean, which is again mu naught as discussed. So, this average value would be the value of mean or the value of mean which you are considering here or the value of mean here, and the plus and minus fluctuations which you would have would basically be of the same quantum, but that would basically depend on two factors. Number one is what is the weightages which you are giving. So, more the weightages they would basically decrease, but the rate of decrease would be slower. Less the weightages in the initial part, their exponential weight decrease would happen at a much not a faster rate, but the overall quantum of weightages which you will try to analyze in next to next reading and so on and so forth, as you basically proceed along the time frame would basically start decreasing. So, we will discuss how to select L and lambda correctly. So, obviously, lambda would mean that you have some intuition based on which you will put the weightages accordingly. You want with this, you want to find out the exponential moving average control charts considering a lambda value of 0.1 and L value of 2.7, and the data are exactly the same as we have discussed. So, these values, let me highlight. So, these are the sample values starting from 1 to 30. These are the xi values which I have already discussed. So, we find out the considering the average of 10, we find out the differences, find out the cumulative sums and do the calculations accordingly. But now only thing which would appear in the cumulative one, we have basically taken the averages. Now, you will basically take the weighted average. So, calculations which are being continued, subgroups 1 to 15 is given, and you give the limits as the values which are given. Now, you basically find out the weightages. So, obviously, weightages would depend on a value of 20% and 80%, that means lambda is 20%, 1 minus lambda is 20%. Based on that, once you do the calculations, you basically find out the values of Zi. Similarly, for the subgroups of 16 to 30, you find out the exponential moving values starting from the 16th one, which is 9.98426 till 10.6341, and you find out the values of the exponential moving average values. So, recall the target value of the calculation was 10 and the standard deviation was sigma is equal to 1. The calculation of the exponential moving average control charts are summarized. So, as they are summarized, you will find out to illustrate the calculations, consider the first observation where x1 is equal to 9.45. So, based on that x1 9.45, you will find out that this value which you are putting is lambda is equal to 0.1, which is about 10% weightages you are giving. This Z naught, which is the previous value, you are putting a weightages of 90%. Based on that, if you do the calculation, Z1 comes out to be 9.945. If you continue doing this, Z2 comes out to be 9.7495, which means, now let me come back. X2 value was 7.99, you will put 10% weightage there, and 90% of the weightages you will put on Z1, which you have already calculated there. So, if you go to say for example, Z3, you will put 10% weightages on X3 value and 90% weightages you will put on this 9.7495. We will continue calculate doing it based on the L value which you have already selected. If I find out the UCL value, it comes out to be 10.27 and LCL value comes out to be 9.73. So, with this we will close the initial calculation for the exponential moving average charts and continue the discussion further in the next class, which will be the 30th lecture. Have a nice day. Thank you very much.